On July 10th, off the coast of Chinese island Hainan, a 5-meter wide rocket booster came falling out of the sky, on purpose. Minutes earlier, it had launched a satellite to orbit. Now it was descending, engine relit towards a waiting ship, but this ship had no landing pad, it had a net. Hooks mounted on the boosters snagged a web of tension steel cables. The cables stretched, soaked up the impact, and the rocket stopped, upright and intact. China had just recovered an orbital-class rocket booster for the first time, using a catching method never attempted anywhere on Earth. The rocket was the Long March 10B, and this was its maiden flight. For an aerospace agency to pull off a flawless booster recovery on a vehicle's very first orbital launch attempt is almost unheard of, historically requiring years of explosive trial and error. And that catch made China only the second nation after the United States to put a payload in orbit and bring the booster home in one piece. So why is every serious space power suddenly obsessed with landing rockets and boosters? Why does SpaceX land on legs and catch with giant robot arms, while Blue Origin targets moving ships? China catches rockets in nets, and Japan quietly hops a testbed 1 meter at a time. What does this race actually decide? For the first 6 decades of spaceflight, every orbital rocket was a magnificent machine used exactly once. Elon Musk made a famous comparison. Imagine throwing away a Boeing 747 after every single flight. That's roughly what expendable rockets do. And the part being thrown away is the expensive part. The first stage carries most of the engine and structure on the Falcon 9. It represents roughly 60% of the vehicle's cost. SpaceX broke that logic in December 2015 when a Falcon 9 booster landed upright at Cape Canaveral. A decade later, the results are staggering. Nearly 600 successful booster landings, and on July 9th this year, 1 day before China's catch, a single Falcon 9 booster flew its record 36th mission. This is what reuse buys: cost and cadence. SpaceX now launches more rockets than the rest of the world combined, largely because it doesn't build a new one for every flight. At separation, a booster is travelling many times the speed of sound, high above the atmosphere, moving away from home. To return, it must flip around and relight its engines against a hypersonic airstream. It steers through the upper atmosphere using grid fins, lattice-like control surfaces that work at extreme speeds. Then comes entry burn, using the engines as a shield against air friction that would otherwise tear the vehicle apart. The final act is the hardest. A Falcon 9 booster can't hover. Even one engine at minimum throttle produces more thrust than the near-empty rocket weighs, so the landing burn is a so-called hover slam, a deceleration timed to hit zero velocity at exactly zero altitude. A second too early, the rocket climbs and falls. A second too late, and it hits the pad. However, every solution to landing carries a mass penalty. Landing legs alone add around 2 tons that come straight out of the payload. That trade-off is exactly why everyone lands differently. Approach 1. SpaceX. Legs and drone ships. Proven, industrialized, boringly routine. But for Starship, SpaceX deletes the legs entirely. The Super Heavy booster flies back to its own launch pad tower, where 2 giant mechanical arms, nicknamed chopsticks, catch it in mid-air. The mass of the landing gear moves from the rocket to the ground. SpaceX has already caught Super Heavy's boosters multiple times and reflown 2 of them. And now its endgame is the Holy Grail. Full reusability, second stage included. Approach 2. Blue Origin. Its heavy-lift New Glenn, a 98-meter rocket with 7 methane-fueled BE engines, landed its booster on Ship Jacqueline in November 2025, on only its second flight while sending NASA's Escapade probes to Mars. In April 2026, it reflew that same booster, becoming the second company in history to reuse an orbital rocket. Approach 3. China. The Long March 10B stands 70 meters tall, burns kerosene and liquid oxygen through 7 YF-100K engines on its first stage, and can lift 16 tons to low Earth orbit while recovering its booster. It's derived directly from the Long March 10, the rocket China is building to land its astronauts on the moon by 2030. And its recovery system follows the same logic as SpaceX's chopsticks. Delete the legs, move the hardware to the ground. Hooks on the rocket, tension cables on rail-mounted dollies that automatically position themselves, and a net, all mounted on a sea vessel. So why does China want this so badly? Beijing is deploying thousands of satellites for its Guowang and Qianfan mega constellation, its answer to Starlink, and expendable rockets simply cannot fly often enough or cheaply enough to build them. Reusable boosters aren't a prestige project, they're infrastructure. The same technology that catches a booster off Hainan is what makes a satellite internet network and a lunar program affordable. And finally, approach 4, Japan. One day after China's catch on July 11th, Japan's space agency JAXA flew its RV-X testbed at the Noshiro Test Center. The hydrogen-fueled vehicle rose 11 meters, translated 16 meters sideways, and landed softly. A hop, not a spaceflight, but a deliberate one. RV-X is the precursor to Callisto, a reusable rocket demonstrator built with France and Germany, and the technology is aimed at a reusable successor to Japan's flagship H3 rocket. Japan is mastering the control problem first, at small scale, before betting the flagship on it. So here's the bottom line. Landing a booster is not the same as profiting from one. Reuse only pays if refurbishment is fast and cheap, and if you fly often enough to spread the savings. SpaceX is the only player that has proven that full loop, hundreds of times over. China now has to show its net-caught boosters can fly again, and almost everyone's second stage is still thrown away on every flight. Only Starship is chasing full reusability. But the direction is unmistakable. Access to orbit is becoming a competition of launch cadence, and cadence is what wins constellations, lunar programs, and military resilience in space. That is why reusability has jumped from one company's obsession to national strategy on 3 continents in barely a decade.